Hello and welcome to the 6.3 lecture. Today we're talking about parallel and perpendicular lines. More specifically, we're talking about the equations of parallel and perpendicular lines. Trying to end up by writing those equations, given some extra information. So the first thing we want to talk about is what are parallel lines? And you've probably dealt with parallel lines in the past. We know them as typically lines that never cross. We say they're lines that never cross. And a little bit beyond that definition, they're lines that never cross, that are living in what we call the same plane. Okay, so and all that's bringing into account is the three-dimensionality of our space. Technically, kind of tough to tell, but these two lines never cross, the two pens that I'm holding. Again, that's a little bit tough to tell because they are living in different planes. Whereas if I look at them from a different perspective, it looks like they cross. Okay? It looks like those two lines cross. But since they're living in different planes, they don't cross. When we force those to live in the same plane, where on one profile you just see one line, now these two lines are in the same plane. If they never cross, then they are what we call parallel. So in order to get an idea of this, let's go ahead and graph these two lines that I have here. The first one I have is y equals 2x plus 5. So we start at 5, go up 2 over 1. Try to make this as painless as possible. And just, again, our goal is to just get that graphed. So let's graph that one. That line looks like, I'm going to try to drag it as far as I can. I didn't like that. Okay. So let me just adjust it a little bit so that we get a better view. And it goes through more of my graph. And let's graph another one at y equals 2x minus 4. So we start at minus 4 and we go up 2 and over 1. Up 2 over 1, that should be enough. So we get a line that goes through here. And now, believe it or not, these two lines are parallel. They're never going to cross. They're never going to, they live in the same plane. They're never going to cross. They're never going to get any closer to each other. They're almost like railroad tracks, okay, in the sense that these two are going to stay the same distance apart forever. Okay. Now there was something that just looking at the two equations that I could have told you that from the beginning. And specifically it came right, let me get a highlighter out. That information came to me right here. The fact that these two lines had the same slope meant that they grew at the same rate. They both have a slope of 2. Somehow this is a slope of 2. And at the same time, this one has a slope of 2. So they rise and fall at the same rate. So they're never going to cross. They're never going to intersect. They're never going to get any closer to each other. So it turns out that a big note for us is that parallel lines have equal slopes. Okay. You might see it written this way, that if you have line A at let's say line A at y equals m1x plus b1, and line B at y equals m2x plus b2. And if they're parallel, then m1 is equal to m2. And actually vice versa. It actually takes a little bit more in math to show both directions, but if these two lines are parallel, then their slopes are equal. But it's a special statement in that if the two slopes are equal, then the two lines are parallel. And again, we typically think of those two things as if one happens, the other happens. Yes, we can't always take that for granted in math. So that's actually a pretty special deal. But that's the big thing. That's kind of the big result, is that the two slopes are equal. Okay, so let's see how we're going to use that. If we want to write the equation of a line that's parallel to a given line, so I'm saying I have some line that's y equals 1/2 x plus 7, and I want to write a line parallel to it. Well, we might think to ourselves, parallel lines have equal slopes. So whatever line I want to write that's parallel to this has the same slope. So my new slope, or for my new line maybe, the slope is 1/2. And then it goes through a different point. It goes through the point -3 too. I'm going to use the y-intercept, the slope-intercept method, I guess. I'm going to rewrite my equation for my new equation. It has to equal 1/2 x plus b. And I'm going to plug my point in for y and x. Again, this is my x coordinate, this is my y coordinate. So put those in where they belong. And maybe we go, I'm going to put them in as red. So my y equals 2 equals 1/2. This isn't the nicest problem, but it's good for us to see that don't always have to be nice and work out to nice round numbers in order for us to do them. So here I get 2 equals 1/2 of -3. I'm just going to call that -3/2 plus b. And we'll go ahead and move up here. And I'm going to copy it down. I can add 3/2 to both sides. Okay. And on the right side they cancel, and that's going to give me my b. Over here, 2 is 4/2. So 4/2 plus 3/2 is 7/2. And so our new equation will be y equals 1/2 x plus 7/2. Again, not a great, nice and easy integer answer, but it doesn't have to be. Okay. So go ahead and pause the video and give the next problem a shot. Hopefully you were able to get that completed. And let's just go through it really quick. I know that my new line is going to have the same slope as the existing line because it's parallel. So we might tell ourselves that m1 has to equal m2 for these two lines to be parallel. And so I get y equals 3x plus some y-intercept b. I'll go ahead and plug in my x and my y and see what we get. So I get 5 for y is equal to 3 times 2 plus b. And now we can solve that. 3 times 2 is 6, so this becomes y equals 6 plus b, and I want to subtract 6 on both sides. Again, you're supposed to pause the video and give this a shot, so I'm not taking all the time in the world to explaining this, but we get b equals -1. And my final answer, 3x minus 1. Okay, hopefully that one went okay. Again, parallel lines have equal slopes. That's the big deal that we should have gotten out of that. Okay. Looking at the next one, perpendicular lines. You can kind of come up with an idea for perpendicular lines, the way we think about them. Kind of generally, perpendicular lines, I'm not going to rewrite it. Perpendicular lines meet at a right angle, or what we think of as a 90-degree angle. It's interesting, kind of history of math a little bit. Right angles used to be a very kind of cornerstone, not to kind of play on words there, cornerstone of angles. We used to not measure angles. We used to just say, is it a right angle or is it something different? And that goes way back in math, but yeah, we didn't know it as a 90-degree angle. We just knew it as a right angle. So let's go ahead and graph these two lines just like we did on the last one to try to see what makes things perpendicular lines. The first one is y equals -2x plus 3. So this is going to go down 2 and over 1 from +3. And maybe we'll put another one on there. Yeah, and I'm using my straight line tool just to make this go a little bit quicker. If you want to use a ruler, I would never hold you back from that. But also, if you want to step out the slope, there's a lot of times that I do that as well and try to get as many points on my graph as I can. So there's my first one, and sometimes I'll even say, this line is right here in red. Let's look at the other one. Let's put it in blue. It starts at -5, and this one goes up 1 and over 2. Up 1 over 2. Up 1 over 2. Again, I know it's nice to have a straight line tool, but it's also a little bit difficult as well. So those two lines, if we were to try to figure it out, they do meet at a right angle. They meet at my 90-degree angle. And so that one there is my 1/2 x minus 5. And so that's kind of the big deal on this, is that these two do meet at what we call a 90-degree or right angle. They are perpendicular. And so was there something that I could use that was given to me in the equations to make note of that? And it's not as straightforward, but it is still the slope. The slope determines the angle of my line, so it only makes sense that my slope is telling me whether they're parallel or perpendicular. Just in this case, it's not, like I said, it's not as straightforward. We do see the number 2 repeated, but we notice that one's positive and one's negative, one's a whole number and one's a fraction. And that's going to be very crucial to determining perpendicular lines. It turns out that perpendicular lines have what we call opposite opposite reciprocal. I spelled that wrong. Opposite reciprocal slopes. Okay, let's kind of break down what those two words mean. The opposite is the plus or minus. Okay, reciprocal flips the fraction. Let's say flips fraction. Okay, so there's no doubt that perpendicular slopes are a little bit harder to find, but there's kind of an easy representation of it. If I have line A, that is y equals m1 x plus b1, so some slope and some y-intercept. Line B will have y equals m2x plus b2, some other slope and some other y-intercept, where the key here is that m1 is equal to the opposite and reciprocal slope. So we say -1 over m2. Okay. So basically, if I'm given a slope of -2, in this one, I think of that as -2 over 1. To get a perpendicular line, I take the opposite sign, so it's going to be positive, and flip the fraction, 1 over 2. And that's how we get from a slope to its perpendicular slope. Again, not as straightforward. The other one was obviously straightforward. It was the same slope. This one, there's a little adjustment that has to be made. This one I've given to us in standard form, which isn't as easy. But the first thing that I'm going to do is turn it into slope-intercept form so that I can see my slope easily. So I'm going to take this and I'm going to subtract 3x, just like we did yesterday. And so I get 5y is equal to -3x plus 12. And I'm going to divide both sides by y. Again, I'm going to divide both sides by 5. So I'm going to have -3 over 5x plus 12 over 5. And now I know that 12 over 5 is ugly and difficult to deal with. I'm just going to move this stuff over. But the beauty is we don't have to really deal with that 12 over 5. We're not concerned about that. All we're really looking at here is my slope. And so I'm going to turn that into its opposite reciprocal. So we might say to find our perpendicular slope, take its opposite, so opposite of negative is positive, and flip the fraction, 5 over 3. Okay, so my new slope will be positive 5 over 3. Put that into my equation, y equals 5 over 3x plus b. Now we plug in our point, -10, 5, and solve for b. So we have -10 is my x. Don't make that mistake. I always have to remind myself that we can work backwards because we have x and y. So 5 is going to equal 5 over 3 times -10 plus b. And now we'll go ahead and solve this for b. 5 over 3 times -10, that's not going to be overly pretty, but that's okay. We're left with 5 on the left side still. 5 times negative 10 is negative 50. Negative 50 over 3 is kind of the best that we can do. So we'll just have to work with it. I'm going to add 50 over 3 to both sides. This is the classic case of I tried to make a problem that worked out really well, but I got a little thrown off when I did it. So I do apologize for that, but we'll see what happens. So 5 in terms of thirds, oops, that's a 50 over 3. 5 in terms of thirds is, we might think of that as 15 over 3. And 15 over 3 plus 50 over 3 is going to be 65 over 3. So we get 65 over 3 as my b, because on this side those cancel, on that side they add, and so we get a new equation. As lovely as it is, y is going to equal 5/3 x plus 65 over 3. So again, go ahead and pause the video and try this next problem. Hopefully you had a chance to get that done. We're going to do the same thing, solve for y first. So I subtract 4x from both sides. Negative 4x plus 10. And I divide everything by 2. So we get negative 2x plus 5. This one looks like it's going to work out a little bit better. Only a little bit though, don't get too excited. So I need my new slope. It's going to be the opposite reciprocal of this. So opposite of negative 2 is positive 2. And flip it over, we get 1/2. So I'll have y equals 1/2 x plus b. Plug in my x and my y. My y is negative 1. My x is positive 1. 1 times 1/2 is just 1/2. So I get negative 1 equals 1/2 plus b. And I want to subtract 1/2 from both sides. On the right side they cancel. And I end up with b is equal to negative 2/2 minus 1/2 is negative 3/2. So I end up with y equals 1/2 x minus 3/2. Again, tried to make a good looking problem, something that worked out really nicely, and it just didn't. So that's okay. But now we've found equations of parallel and perpendicular lines. Make sure you go ahead and summarize those notes. And as far as expected problems for you to do, I've got a little less on the practice, a little more on the application this time. So practice, I just want you to do numbers 1, 2, 11, and 12, and then application problems 3 through 9. There is the application walkthrough video that should be attached as well, if you want to take a look at that. Okay, 3 through 9 is all about putting a bunch of lines on this graph and seeing what we get. It's a little bit involved, but there's a little bit of review in it as well. Okay? Make sure you get those problems done, get the Mastery Challenge passed. Have a good day, and we'll see you in class.